Hello, ladies and gentlemen. You are about to go on a long journey discovering periodic trends. So, make sure you have a periodic table in front of you, preferably a hard copy that you can write on and draw these trends on would be helpful. So, you might want to pause this video now and get that. All right. So, yesterday, or the last time I saw you, we talked about metals, nonmetals, and metalloids. So let's rehash that a little bit. When you look at your periodic table, you have metals, these blue ones, nonmetals. Remember, hydrogen counts as a nonmetal, and then more nonmetals over here. Then we had our metalloids. We marked them on your periodic table already, right? So the trend for this is that things tend to get more metallic as you go to the left and down. So nonmetals are in the orange, as we just said. Doop, doop, doop. There they all are. So hopefully you can do all these from what we talked about the other day. Identify a metal. What are its properties? So it's lustrous. It's a good conductor of heat and electricity. It is malleable, right? And then let's take a quick look at them here. Metals are lustrous, which means shiny, malleable, ductile, good conductors of heat and electricity, usually solids at room temperature. One exception to that, of course, was mercury we discussed. Nonmetals were the opposite, dull, brittle, not good conductors, which means insulators. And some are solid, but a lot of them are gases. Bromine's the only liquid. So metalloids or semi-metals are those ones that ride the little staircase there we talked about. They can act like both. They can be shiny but brittle. They might, under some circumstances, act like a metal, others act like a nonmetal. So the semiconductors are one of the most important ones of those we use in computers and technology. So let's look at trends today. So first trend we're going to talk about is atomic radius. So radius in math, would be the distance from the center to the edge, right? Well, if we're doing atoms, yeah, you want the distance from the nucleus at the center to the edge. But remember those whole electron cloud things, we just have those probabilities. There's no definite edge. So how are we getting an edge? How are we going to measure a radius? We tend to measure what we call a covalent radius. So we take two of the same atom bonded together and then measure the distance from the two nuclei and divide it in two. These are usually picometers or angstroms. So let's take a look at what that looks like. So here you would have two atoms bonded together. So here's one nucleus, here's another nucleus. Those are fixed points that we could measure, right? And so you can measure the distance between those, divide that in two, and now you've got a radius. So that's how we measure the covalent radius of atoms. These were two bromine atoms, by the way, in this example. So what's the trend? Well, trend for the radius in the vertical column is to go down. So they're smaller at the top, larger at the bottom, which should make sense to you if you think about the Bohr model. Each step you go down in the family, you're adding a new, that's potential energy level or primary energy level, to the electron cloud, which is going to make it bigger, right? So if you go back to our Bohr models, just for ease of representation, the first level is as close as the electrons can get to the nucleus, but it only holds two. So any more you add are going to have to go out to the second energy level, and then they can hold, 8. And then if you have more, they're going to have to be further out. So all electrons would like to be near the nucleus, but there's not that much room. So they go in these energy levels that we discussed and get further and further away. So as you go down the periodic table, you're adding a new level. This is level 1 on the periodic table, level 2, level 3, level 4, level 5. So obviously things are going to get further and further away, making the atom bigger as you go down. Now, what about going across horizontally? This is a little trickier, a little less obvious. What happens to the atomic structure as we go from left to right? So let's take a look at that. For each step you go from left to right, you're adding a proton, right? And an electron. Now, you're adding the proton to the nucleus, the electron to the electron cloud. So electrons that you're adding are still going to be in the same energy level or sublevel, right? So they're not any further away from the nucleus than the electrons that were already there. On the other hand, you are making the nucleus more positive. So you're going to have a more positive nucleus and a more negative electron cloud. So higher positive charge, a higher negative charge. And they're not any further apart, which means it's going to feel like stronger magnets pulling on each other more. So this increased attraction is going to pull the cloud in and make it a little bit smaller as you go across from left to right. So let's take a look at what that might look like. So again, we have the effective nuclear charge, right? That pull on the electrons from the nucleus. And the closer an electron is to the nucleus, the more it's going to feel that pull. So things very close to the nucleus are really feeling a strong pull from the electrons are really feeling a strong pull from the nucleus. So as effective nuclear charge increases, the electron cloud gets pulled tighter as you go across. So if you look at your periodic table, so look at row 2, right? You've got lithium. So here are your electrons in that S cloud, right? You go to beryllium. You've added a stronger positive and you've added more electrons in the cloud, another electron in the cloud. So it's going to pull a little tighter. And then, well, we'll go on from there. So they're going to, this isn't the best picture because it's talking about ions, but just to give you an idea. So these two are going to be pulled a little bit tighter. And then now when you go over to the P block and you hit boron, well, you've kind of added a P in there. That P orbital might make it increase a little bit. So let's look at the trend. So yeah, they get smaller as you go across here, as everything's still being added in the same energy levels. But notice when you hit the P, there's a little bit of a jump here. It gets a little bit bigger because you added that P orbital. And then as you add more to the same P orbital, things tend to get smaller. So these trends aren't absolutely perfect. There's always going to be exceptions to rules on these. But in general, the trend is going to look like this for atomic radius. You might want to draw these on your periodic table or in your notes, make a little diagram. So as you go down, they tend to get larger. And as you go to the left, they tend to get larger. So things tend to get larger on the periodic table as you go down to the left. So the biggest thing on the periodic table would be francium. The smallest would be up here, your helium, right? So if I were to give you two things and ask you to tell me which was larger, sorry, I might say, okay, which is bigger, potassium or calcium? And you would say, okay, they get smaller as you go this way, so potassium would be bigger, right? Or I might say, which is larger, oxygen or fluorine? See how they get smaller that way? So oxygen's larger. So which is larger, oxygen or sulfur? Oh, well, sulfur would be larger because it's got another level on it. So you're going to use these trends to compare and tell me which is bigger or smaller. Now let's talk about something called shielding. So as you add more energy levels to an atom, the inner layers are going to be shielded, or sorry, the inner layers are going to shield the outer electrons from the nucleus. So what does that mean? You think of a shield like blocking, right? Like it's in the way of something. So the effective nuclear charge on the outer electrons is going to be less because there's so many things in the way between the outer electrons and the nucleus. So we talked about, that pull of the nucleus on the electrons. The farther away they are, the less they're going to feel that pull because of all those electrons in between. So they're going to be less tightly held, if that makes sense to you. This is important for ionization energy. Let me go give you an example. If we were in the classroom, I'd use right now would be my cell phone, right? So if my cell phone is in my pocket, then it's very close to me. I know where it is. It's very hard to get that cell phone away from me. Like if you were going to try to steal my cell phone, I would notice, right? I'm attached to it. But if I put my cell phone on one side of the room and, the classroom's all full of kids and I walk away, then there's a lot of kids between me and my cell phone, then I am not as tightly connected to that cell phone. It would be a lot easier to steal that cell phone because it would be shielded by all those things in between us. So that's going to go into this trend we're talking about, ionization energy. So, ionization energy, if an electron is given enough energy, so you hit it with a photon, it can overcome that effective nuclear charge that's holding it in, and it can leave the atom completely. Okay, so you have ionization energy is the energy required to ionize that atom and remove an electron. So the number of protons and electrons is no longer equal anymore, right? So if you remove an electron, now you have more protons than you do electrons. Now you've got a charged ion. So the energy required to remove an electron, that is the ionization energy. We measure it in kilojoules. The larger the amount is, the larger the atom is, the easier its electrons are to remove. So this sort of goes with the shielding effect I just talked about. The bigger something is, the farther away that outer electron is, the less it's pulled on by the nucleus, and the easier it will be to steal, right? So ionization energy and atomic radius are inversely proportional. If your atomic radius is large, it takes a small amount of energy to steal the electron. So ionization energy is always endothermic. What does that mean? That means it requires energy to remove an electron. Everything on the periodic table, the electrons are there because they're being pulled on by the nucleus. So you're going to have to put some effort into removing it. That means it's going to take some energy to remove an electron. Some, it won't take much energy, but it will take some. So let's think about as you go down a group here. So hydrogen has its electron very close to its nucleus. It's going to be hard to take that away, right? Because hydrogen's like, well, we're right here. I got that electron. It's pretty close to me. But lithium, its outer electron, has got a little shielding between its nucleus and its outer electron. So that one will be easier to take than hydrogen. So it'll take less energy to steal this than it will this. Keep going down, look at sodium. This electron is, 3 levels away. So it's going to take even less energy to steal that electron. And if you went all the way down to francium, where that outer electron is like 7 levels away, it'd be easy to steal that one, right? So that's why they are going to get more reactive. Remember, we said that the other day, they get more reactive as they go down. That's because it's easier and easier to steal those outer electrons. Same with group the alkaline earth metals. And over here into the, even on the other side of the periodic table, the halogens, they don't want to lose their electrons at all, but they still could. It would take a lot of energy to get them away, but it would take less energy the bigger they are. So this leads to our other trend with ionization energy. So ionization energy decreases as you go down, okay? But remember how we said it was inverse to size. So things that were bigger were easier to steal from. Things that are smaller or hard to take things away from. And that's the same thing you see here. So remember, things get smaller as you go across this way, and their ionization energy greatly increases. Look at helium. There's nobody's taking an electron away from helium very easily, right? Fluorine, chlorine, all these guys over here, the noble gases, they're not wanting to lose. They have like the highest ones over here because they're not losing their electrons. They don't want to get rid of them at all. These guys don't want to, but it's a little bit easier than the noble gases. Again, they don't want to, but it's easier than these. So the overall trend for ionization energy, oh, sorry, we talked about drawing the arrows on a sheet. If you have it, hang on, there we go. It's going to increase as you go up and to the right. So opposite of size, right? Size increase the other direction, but the bigger something is, the easier it is to steal from. So ionization increases as you go up and to the right. So if I said, what has a higher ionization energy? Magnesium or calcium, you'd say, oh, magnesium has a higher one because it's smaller. Or what has a higher ionization energy? Fluorine or francium. And you say, oh, definitely fluorine. It's so tiny and it has its electrons close to it and it doesn't want to lose them. All right, electron affinity. So let's think about that word affinity. What does affinity mean? I have an affinity for chocolate. So I like chocolate. I like to get chocolate, right? So electron affinity is the energy change that occurs when an atom gains an electron. So where ionization is always endothermic, meaning it always takes energy to get an electron away from something, electron affinity is usually exothermic, meaning they go down in energy, right? So it's not always the case. We'll talk about the exceptions here. So electron affinity is exothermic if there is an empty or partially empty orbital for an electron to occupy. But if there's no empty space, then the orbital is going to have to create another energy level. That's going to take energy to do it. So think about a hotel here when we talked about, them being like in a hotel. If I have to go build another floor on the hotel, that's going to require energy. Whereas this scenario up here, I've got an empty hotel room. I can just put you in there and it's good for me to put you in there. So it's going to be exothermic. It's not going to require anything from me. I'm going to benefit from it. So this is true for alkaline, this one that's endothermic here, that's the alkaline earth metals and the noble gases. So if you're an alkaline earth metal and I'm trying to give you another electron, we're going to have to open up the p orbital. So that's not going to make you very happy. So it's going to require energy to make the p orbital, right? For noble gases, I'd have to put on a whole other energy level. They're not going to like to do that. So alkaline earth metals and noble gases don't really have that electron affinity like other things do. Now, who on the periodic table would really like to gain other electrons? Well, these halogens over here, remember, they're just one away from being a noble gas. So they really like to gain electrons. It's really in their benefit to gain electrons. These guys over here would rather lose. It's easier to lose things, but they tend to lose things, but they can put another electron in that open s orbital, These Ds can put other electrons in there. It doesn't hurt them, but that affinity for electrons really increases as you go this way. So if you think of affinity as wanting electrons, the one on the periodic table that wants electrons the most would be the fluorine here, right? The one that wants them the least, well, would be the noble gases and the alkaline earth metals, but also francium really doesn't want any more electrons either. So electron affinity increases as you go up and to the right. But again, remember those noble gases are like, no, they are not more not a higher electron affinity than, say, the halogens. So the trend would stop there. Metallic character, we already talked about, increases as you go down to the left. So things get more metallic, meaning metals like to lose electrons. So they get more likely to lose electrons if they're bigger and don't want electrons. So that would be francium. Big guy with a bunch of electrons shielding his outer electron. There's no way he's going to add more in there unless somebody's just really forcing them on him. So he'd rather just get rid of that one and be a noble gas. It would be easier. All right. Electronegativity is the measure of an atom's attraction for another atom's electrons. So this is more than just, I want some electrons, I like having other electrons. This is, I like to steal other people's electrons. So electronegativity is how good is an atom at stealing electrons. So think about who would make a good thief, right? You think like a sneaky little cat burglar. Would be a good thief. So we use a scale from 0 to 4 to judge electronegativity on the periodic table. These are Paulings, if you're looking for the units. And generally, metals are electron givers. So they're not going to be good at stealing, right? They're going to have low electronegativities. On the other hand, nonmetals tend to be electron takers. They want other people's electrons. So they're going to have high electronegativities. So, what about noble gases? Of course, they don't want anybody's electrons and they're not giving up any electrons. So, they are going to be the zeros in this scenario. So, noble gases are like 0 on electronegativity. They're like, nope, leave us alone. We're not doing any of this. The highest fluorine here would be a number 4. So why is he such a good thief? Think about fluorine. He's tiny, right? His electrons are close to his nucleus, and he wants other people's electrons. How's he going to get them? He's got to get his nucleus close to their electrons. So since he's so small, he doesn't have that shielding effect. His nucleus is going to have a stronger pull on other people's electrons than something bigger might. So he makes a great little cat burglar right here, fluorine. On the other hand, big, clumsy francium down here, not going to be a good thief at all. Probably the worst thief, right? He's like stuck in the doorway or something. So he's big. He's got all these electrons shielding his nucleus from anything he might even want to take. So he's going to be really bad at this. Not quite a 0 like the noble gases, but really low. So fluorine would be the highest electronegativity with a 4. Noble gases are 0, but otherwise the trend is going to decrease as you go down to the left. Overall reactivity. So let's combine all these trends together. You kind of have to treat metals and nonmetals separately in this instance. So what makes a good metal? Something really metallic, a really reactive metal. So metals, the most reactive metals are going to be the big ones like francium because they're shielded, their outer electrons are shielded, they're trying to be electron givers, and those electrons are going to be easy to steal, right? On the other hand, nonmetals are trying to take electrons. So their most reactive ones are going to be the smallest ones, like we just said with fluorine. So if you look at the periodic table, you kind of have to divide it up into metal versus nonmetal. So the most reactive metals are going to be the big ones down here, your francium, and the most reactive nonmetals are going to be the small ones up here, the fluorine. So reactivity is sort of a combination of all those other trends put together. Why are any of them doing this? Remember, the goal was to get that octet, to have that full valence shell. So to get the full valence shell, some are going to steal electrons, some are going to give away their electrons and get rid of the extras. When they do this, if they're taking electrons or giving electrons, They might do this by bonding with other atoms, or they might do this by stealing from other atoms or giving to other atoms. If they gain or lose electrons, they're called ions. Okay, so let's take a look at what ions are. When an atom gains an electron, it becomes negatively charged. So now it's going to have more electrons than protons. Remember, electrons are negatives. So we're going to call that an anion. In the same way that a non-metal atoms can gain electrons, metal atoms can lose electrons. So some like to gain, some like to lose. If they lose electrons, remember they're losing those extra negatives, they're going to have more positives, so they're going to make positively charged cations. So ways to remember this, here's Anne. She's so unhappy. She's so negative, right? Then there's a cation. He's a plussy cat. I also like to remember that cation has a T, which kind of looks like a positive sign in it. Cats have paws, they're positive, things like that. Whatever helps you out. Cations are always, let's talk about the size and the radius. So cations are always going to be smaller than the original atom. What's happening here? They're losing an entire energy level, right? They're shedding that outer layer to go down to their inner core. So they're going to get smaller, right? Anions, on the other hand, are always going to be larger. They're going to gain an electron. So they're adding extra electrons to their outer level, which is going to make a stronger negatively charged cloud, but they're not getting any more positives in the center. So it's not going to be able to hold on to them as tightly. So, example here. So here's your sodium atom. When we say an atom, we mean, protons and protons and electrons are equal. When it becomes a sodium ion, it's shed that outer layer, right? Why would it do that? Well, maybe it met up with chlorine. Sodium had this one it wanted to get rid of. Chlorine wanted one more to fill its outer shell. So sodium transfers that electron over to chlorine. Now sodium gets smaller because it shed that outer layer. Chlorine gets a little bit bigger because now it's like poofed up a little bit. It's got an extra electron. Now they're held together because one's positive and one's got a negative charge and opposites attract. So now we have made an ionic compound, okay? We have a positive cation and a negative anion attracting one another. That's an ionic compound. More to come on that later. So cation formation, here's a cation. Starts off, with that extra electron in the outer one. Wants to get rid of that. When it does, boop, it gets smaller. So cations are smaller than the atoms. On the other hand, here's the anion. You've got almost full outer shell. You're going to add a new electron to that. Push in there. Oh, dang it. My animation didn't work. When you add that to that, it's supposed to swell up a little bit, but it didn't. Oh, well. Then we've got, so let's recap everything. This is like recap for the lesson. You've got your atomic radius, right? So the distance between the two nuclei bonded together divided by 2, right? It decreases across the period because you're going to pull things in tighter as you go across. It's like a stronger magnet. It increases as you go down a group because you're adding more shells and energy levels to it. So atomic radius increases as you go down, decreases as you go across. There's your trend. Hopefully you have it written down. Ionization energy, this is the energy required to remove an electron from an atom, tends to increase as you go across. So as things are getting smaller, they're harder to remove. Opposite of radius, right? So it decreases as you go down. As they get bigger and bigger, they're shielded, they're easier to remove. So ionization energy increases as you go to the right, decreases as you go down. Then there was electronegativity. This is the measure the ability of a chemical compound to attract electrons. So how good are you at stealing electrons? And you have the radius increases, the electrons get closer to the bonding atom's nucleus, right? So electronegativity tends to decrease as you go down or remain the same. As a radius increases, electrons are farther from the atom's nucleus. So again, with the electronegativity, it's going to increase as you go across, except for the noble gases, right? They're not in this game. And decrease as you go down. So highest electronegativity, fluorine, right there. So there they all are on one chart. And then again, we talked about cations and anions. Cations are positively charged ions formed when an atom or metal loses an electron, and it's going to be smaller. Anions are negatively charged ions formed when nonmetals gain electrons, and they're going to get larger. Okay, so we will, again, here's that picture I was using earlier with the the ions. So as you go across, the lithium ion is going to be smaller than the atom, and the oxygen ion is going to be larger than the oxygen atom was, because its cloud is being held less strongly by the nucleus. All right, we'll stop there, and good luck.